You probably know about dy dx, but you know what this is? What about this? And what about this? I was joking about the last one, but you should know the rest. So first, let's talk about derivatives. Suppose we have a function y x equal x squared. What would be the derivative of this function? Okay, this is very insulting to your intelligence. I'm sorry. Everybody know it is dy dx, right? The change of y with respect to x, and the answer is 2x. So far so good. But what if we have a multivariable function y depend on x and s equal to x squared? So what would be the derivative, or more correctly, derivatives of this function? Okay. If you write dy dx, this doesn't make sense anymore in this context. Okay, you need to be more specific. And by being more specific, it means that you need to say, now we have the change of y. So notice that we use this curly thing called partial derivative with respect to the change of x now. So see, we don't use this d anymore because we have two variable now. Okay. By writing a curly thing like this, you implicitly assuming that s is treated as a constant. And I'm just gonna write it like this. So if you write, if I write something like this, it means that s is a constant. So in thermodynamics, it's quite important to explicitly say that something is a constant. So if you can perform this derivative by just looking at it. So it's gonna be 2sx. Okay. Another derivative that you can do is the change of y with respect to the change of s. And you implicitly assume that x is a constant, but I'm just going to write it out explicitly again, okay? And the answer is just going to be x squared, okay? Next, let's talk about differential. Again, we have the function, a single variable function, and what is the differential called dy, okay? So the way I look at it is that dy is just the change of y. So what would you set it equal to, right? So since y is a function of x, then it makes sense to just say that the change of y depends on the change of x. But then, y is not x, so you need something in front of it. It's like a weight, or it's like a rate of change, right? So the rate of change is dy dx, okay? So it's just basically saying that, the change of y equal the change of x times some adjusting constant, basically, okay? And you can calculate this, because you know the functional form of y. So you're going to say dy equal 2x dx, okay? So this is, how we write differential. Okay, so next we have a multivariable function again. What would you write dy then, okay? dy, because y is a function of both x and s, it makes sense to just say that the change of y depends on the change of x plus the change of s, okay? Let me change the color, okay? Now, you need some adjusting constant again. So in before you have the derivatives, right, the d. Now, you might guess that will be the partial derivative. So you would need the adjusting constant in front of the dx. You would have partial y, partial x, okay? And I'll just stick the s in here just to saying that in this evaluation s is a constant, okay? And in front of ds, the change of s, you would have the partial of y with respect to partial of s. I'm just gonna stick x in here just to say that x is a constant, okay? So now, I think it makes sense for me in a way that, the change of y depend on both the change of x and s, but with some adjusting constant. The adjusting constant, is calculating from the partial derivatives. Okay, so let's just write this out in the functional form. So dy equal to, so you have partial y, partial x, so you have 2sx dx plus, so partial y, partial s is simply just x squared dx. Okay, so this is how you write the differential, dy for the multivariable function. A lot of places also call the total differential too. This is also what they call. So apart from the concept of differential, there is also a concept of difference. Okay, so differential is denoted by dy, but then difference is denoted by this triangle called delta. So this is delta y. Okay. Differentials and difference are both changes, but for differential, this is the change that is infinitesimally small. So it's so small that it's practically no change. Also, another way to say it's a change without change. Okay, so if that sounds confusing, welcome to thermodynamics, because it's gonna get a lot more confusing. But the concept of something that change without change is like the backbone of thermodynamic formulation and concept. So you kind of have to get used to it, Differential is the idealized concept. It's something that you cannot be observed. Okay. Difference, on the other hand, is the change that you can observe in your everyday lives. So it's the real change. It can be observed. Okay. Another question that you might ask is like, okay, so how does differential and difference related? You can go from one thing to the other thing by doing integration. Okay. So let me give you an example. If you have a differential y equal to s dx plus x ds, okay, you can work it out, but essentially the function y is just x kun x, okay? If you do some integration, so let's say you integrate dy from the point A to point B, what you would get is a difference. So the difference is just the functional form of y, xs evaluate. So this, when I write something like this, it means evaluate at the point B. Subtract by the function y, evaluate at point A. So essentially, different is just the final point, subtract by the initial point, essentially. Okay. So this would apply to certain cases, but actually not always. Okay, this is not always correct because there are two types of differential. There are two types of differentials. One is exact differentials, and the other one is inexact differential. So let me show you the example. So for exact differential is something we saw earlier, like dy equal to s dx plus x ds. Okay, so this differential is exact because you can potentially find a function whose differential is this form. Okay, y equal to xs. Okay, on the contrary, inexact differential, if I were to put this x, in front, of this coefficient, just one x, and I'm asking you to find the function whose differential is this form. Even if you write all the function in this universe, you will not find a function y that gives you this differential. Okay, so that's how the inexact differential is defined. Okay, so back into this diagram. So if we have the exact differential dy, okay, we know that this is exact. If we integrate it from a to b, then you will get difference. Okay, so this is something that we saw before, right? Difference is just y evaluated at b, subtract by y evaluated at a. Okay, but then if you have inexact differential, this is another scenario. First, we write inexact differential as this delta. So this is the small delta. So the triangle is the capital delta. So I'm probably gonna use the word delta a lot, and I'll try to make it clear, which one is which. But in this case, this is delta y. This is inexact differential of y. Okay. You can of course integrate this differential from a to b, no problem at all. But the difference is that the things that you will get after the integration is not the difference. It's not the difference. It's just something else that is not differential. So you have differential, you do something to it, you integrate, you get something that is not differential. Okay, it's just silly like that, but it's not different. Okay, it just so in our class, our subject we're probably gonna call just y. So y is just something that is not delta y. Okay, just integrate delta y, you get y, the something. Okay. Another very important things that come out of this is that if y, if dy is the exact differential, when you perform this integration from a to b, okay, it doesn't matter what path you take, you will always get the same value difference. You always get the same difference as long as your initial and final points are the same. So as long as a and b is the same, doesn't matter what path you take, you always get the same value, the same thing out, the same difference. And this is called the path independence property of the exact differential. Okay. On the other hand, if you have inexact differential, this delta y, if you integrate from a to b, okay, if you keep a and b the same, but you change the path, what you get, the result y, it will be dependent on the path. It will be different depending on the path you take, even though a and b is the same. And this property is called the path dependent. Okay. Another thing is that if you have y, the variable y whose differential is exact, we call this y, a state function or state variable. Okay, let me say that again just to make sure. Okay, so if you have a quantity y whose differential is exact, we call this y a state function or state variable. Okay. On the other hand, if you have y whose differential is inexact, then you would call this y a path function or variable. Okay. So why bother about this differential concept? So the reason that I introduced this concept so early in the course is that it used a lot in the fundamental thermodynamic work. So the fundamental thermodynamic work, or essentially the formulation of like thermodynamic law, for example, is based on investigating a certain quantity that is useful to us, right? So the first law, for example, investigating internal energy, let's say U, but we don't know about that at this moment, right? We just say, okay, there's some quantity that might be useful to us, okay? And a lot of experimental work, a lot of thinking has gone into proving that U is a property of the system, and that the change of U does not depend on path. So does that sound familiar? Something that is a state function and U and has path independent property. So essentially it's just proving that U is a state function and that du is an exact differential. So see, a lot of work has gone into proving that du is an exact differential. Okay, and once you know this property of this du, the exactness of du, then then a lot of the formulation follow. For example, you can write a lot of equations, use a lot of tricks into writing du as a function, as expression of other state variable, for example. Another very powerful thing is that you can calculate the change of U. So I just told you that U is an energy, and energy is it's an abstract quantity. Like we don't have device that measure energy, but we can measure energy by indirectly measure something else. Like we measure temperature, we measure volume. And in order to relate the change of volume and pressure into the change of energy, we are exploiting the property of exact differential of U, essentially. So this is a very powerful concept and allow us to calculate many abstract quantity in thermodynamics. And of course, we have the path independent properties, so we can calculate the change of U even if we don't know the path, or we can just imagine an imaginary path, and that makes our life easier in calculations or in conceptualize the change, for example. So I hope that you learned something about differential today, and I hope that this concept will help you understand the fundamental work that you will learn about in this course in the very near future. See you later.